Let's start with a simple idea. Imagine you are walking towards a wall. You decide to play a game. First you walk half the distance to the wall, then you walk half of the remaining distance. You do this again, and again, and again. In your mind you can keep taking these smaller and smaller steps forever. You will get incredibly, unbelievably close to that wall. You'll get so close that the distance is practically zero, but you will never technically touch it. This idea of getting infinitely close to a value without ever quite reaching it is the core concept of a limit. It's a way for us to talk about what happens at a very specific point by looking at what happens right next to it. In mathematics, we often run into situations where we can't just plug in a number. Maybe we have a fraction where plugging in a certain value for x would make the bottom part, the denominator, equal to 0. And we all know we can't divide by 0, it's undefined. This is where limits become our superpower. Instead of trying to evaluate the function exactly at that tricky spot, we can ask a different question. We can ask, what value does the function get closer and closer to as x gets closer and closer to that tricky number? The limit is that target value, the destination your function is approaching. Think of it like a video you are watching. Let's say you want to see the exact moment a baseball hits a bat. If you pause the video, you just see a single frozen frame. But, to understand the impact, you want to see the frames just before and just after. You want to see the motion leading up to that point. A limit is like looking at the frames that are infinitesimally close to the moment of impact to understand what is happening right at that instant. It allows us to analyze points that are otherwise impossible to calculate directly, giving us a powerful tool to handle infinity and undefined points with precision. So, why do we need this? Limits are the fundamental building block for the rest of calculus. Without a solid understanding of how to approach a point, we can't talk about how things change from one moment to the next. They are the foundation upon which the ideas of derivatives and integrals are built. They let us move from the world of simple algebra, where things are static, into the world of calculus, which is all about motion, change, and the dynamic relationships between variables. Mastering this concept of getting close is the first major step into a much larger and more exciting mathematical universe. Now that we have the idea of a limit, we can build on it to understand something truly exciting, the derivative. Imagine you are driving a car on a long road trip. If you travel 120 miles in 2 hours, your average speed is simple to calculate. It's 60 miles per hour. But we know that you didn't drive at exactly 60 miles per hour the entire time. You sped up, you slowed down, you stopped for a moment. What if you wanted to know your exact speed at one specific instant, the moment you looked at your speedometer? That exact instantaneous speed is what a derivative tells us. It's the rate of change at a single point in time. So how do we find this instantaneous speed? This is where limits come back into play. To find the speed at one moment, we can start by finding the average speed over a very, very short period of time. For example, the average speed between 1 second and the next. Then we can make that time interval even shorter, 1/10 of a second, 1/100th, a millionth. We are using a limit to shrink the time interval until it is infinitesimally small, practically zero. The derivative is the limit of that average rate of change as the interval we are measuring over shrinks to nothing. It's a slope, but not the slope of a line between 2 points. It's the slope of the curve at a single point. Let's think about this visually. If you graph your car's distance traveled over time, you'll get a curve. The average speed between 2 points in time is just the slope of the straight line connecting those 2 points on the graph. As you bring those 2 points closer and closer together, that connecting line gets closer and closer to becoming what we call a tangent line, a line that just touches the curve at a single point. The slope of that tangent line is the derivative. It represents the steepness or rate of change of your graph at that one specific location, giving us a precise measure of how fast something is changing at an instant. This concept is incredibly powerful and appears everywhere in the real world. In physics, the derivative of a position function gives you velocity, and the derivative of velocity gives you acceleration. In economics, it can be used to find the marginal cost, or the cost of producing just one more item. In biology, it can model the rate of growth of a population of bacteria. Anytime you want to know how fast something is changing, not over an hour but right now, you are asking for the derivative. It turns our static graphs into dynamic stories of motion and change. We've seen how derivatives break things down to find an instantaneous rate of change. Now let's look at the reverse process. What if we know the rate of change at every moment and want to figure out the total amount that has accumulated over time? This is where the integral comes in. If the derivative is about finding the slope at a point, the integral is about finding the total area under the curve. They are two sides of the same coin, a beautiful relationship known as the fundamental theorem of calculus. The integral is essentially a process of summation. Let's go back to our car example. Imagine you have a record of your car's exact speed at every single second of your 2-hour trip. How could you figure out the total distance you traveled? You could approximate it. For each second, you could multiply your speed during that second by the time, 1 second, to get a tiny bit of distance. Then you could add up all those tiny distances for every second of the trip. This would give you a pretty good estimate of the total distance. The integral takes this idea to the extreme, doing the work of adding up an infinite number of infinitely small pieces. To make this process perfect, we imagine slicing the area under our speed versus time graph into an infinite number of incredibly thin rectangles. Each rectangle's height is the speed at that moment, and its width is an infinitesimally small slice of time. The area of each tiny rectangle represents the tiny bit of distance traveled in that tiny instant. The integral is the tool that allows us to sum up the areas of all of these infinite skinny rectangles to find the exact total area under the curve. This total area represents the total distance traveled. It's a way of accumulating a quantity from its rate of change. This idea of summing up infinite tiny pieces is just as useful as the derivative. Engineers use integrals to calculate the total pressure on a dam by summing up the pressure on tiny horizontal strips from the top to the bottom. In finance, they can be used to calculate the total accumulated value of a continuous stream of income. Medical professionals can use them to determine the total amount of a drug that has been absorbed into the bloodstream over time. Whenever you have a quantity that is changing, and you want to find the total accumulation, you are thinking about an integral. So we have these three big ideas: limits, derivatives, and integrals. They aren't just separate topics you learn in a math class. They are deeply connected and tell a complete story about change. The limit is the foundational concept, the language we need to talk about the infinitely small. It's the microscope that lets us zoom in on a single point on a graph and understand what's happening there. Without the idea of getting arbitrarily close to a point, the precise definitions of the other two concepts would be impossible. The limit is the starting line for the entire journey of calculus. From limits, we get the derivative. The derivative uses the limit to look at the slope between 2 points as the distance between them shrinks to zero. This gives us a tool for deconstruction, for breaking down a smooth, continuous motion into its instantaneous rate of change. It answers the question, how fast is this changing right now? It takes a total amount function, like total distance traveled, and gives us a rate function, like instantaneous speed. It's the process of finding the slope of the curve at every single point along its path. The integral, in turn, does the exact opposite. It is a tool for reconstruction. It takes a rate function, like speed, and adds up all the tiny pieces to rebuild the total amount function, like distance. It answers the question, given how fast it was changing, what is the total accumulation over a period? The integral uses the idea of summing up an infinite number of infinitesimally small parts, a concept that itself relies on limits, to find the total area under a curve. It is the perfect inverse operation to the derivative, allowing us to put the pieces back together. Together, these three concepts form the core of calculus and provide a powerful framework for understanding the world. They allow us to move from static algebra to the dynamic study of change. Whether it's modeling the trajectory of a spacecraft, predicting population growth, designing a bridge, or understanding financial markets, the principles of limits, derivatives, and integrals are at work. They give us a way to precisely describe, analyze, and predict the behavior of systems that are in constant motion, making them one of the most significant and practical achievements in the history of human thought.